Okay, I'll try to keep it short. So yeah, my name is Richard von Seck, and this talk is mainly based on a paper that we had submitted in NCA in the 21st NCA last year. And as Philip already introduced, the main focus of my research is based more towards permissioned blockchain systems or permission consensus systems, but of course, to some extent, it also applies to more open or bigger scaling systems. So to go back to the original motivation why we need consensus or state machine replication, basically is because we want to introduce some robustness, right? So if you have a basic system with a client and a server, then the reason why you want to introduce or the main problem that you have is if the server malfunctions, then the system is not working, right? So what you do is you introduce replicas on which the state or the computations are replicated. They're done in a redundant fashion. So when some of the replicas don't work, they behave, they crash or they behave faulty, then still through a majority vote, the system overall is able to provide a correct response to the client, right? So effectively, the state needs to be synchronized, and this can be everything, like a blockchain system, could be transaction data, could be something else. So the classical problem with this is, of course, that it introduces a lot of overhead, right? So the one of the seminal permission consensus protocols, the PBFT protocol, we have a communication protocol or profile that looks roughly like this. So you can see we have the client sending a request, and then the consensus process, it pretty much escalates pretty quickly, and then the end, the client gets the requests. So there are, of course, efforts to also use this originally permissioned or BFT-based consensus for blockchain approaches, but the main problem of these is they don't scale too well, and there's still ongoing research, basically, that since 40 years to improve this, right? To improve performance and scalability properties. So addressing this, there, as soon as 2007 or 2010, on multiple fronts, basically, it was attested that already at that time, the state of the art is distressingly complex. It's hard to design protocols that work for a lot of different use cases. And if the protocols are developed, then usually they're notoriously difficult to develop, test, and prove, right? So if our goal is to optimize these protocols anyway, then it would be great if we could avoid introducing additional complexity, and at the same time, if we can avoid introducing breaking changes to provably secure protocols, right? So based on this motivation, the goal for our talk is basically, or the things that we try to do in this talk is we want to outline the feasibility and impact of building block optimization for BFT-SMR systems. We provide a small systematization of practical BFT-SMR systems in terms of their networking architecture, and we'll do a short case study discussion, depending on the time that is left, for an exemplary protocol, namely the hot stuff protocol. Okay, so building block optimization. Why do we want to do this? Well, the idea is if we find common building blocks or common assumptions, as Professor Tessona already introduced, there's a lot of hard assumptions on these protocols usually, which is nice for the protocol designer, but for the actual implementation, usually it creates some challenges, right? But if we do it right and we find the right optimization, then if the assumptions are still fulfilled, we do not actually restrict safety and liveness, and also a nice effect on the side is that the optimization in theory applies to all systems that use this building block, right? So taking a look at the related work, so we basically took a look at a lot of systems, and we identified 3 common, very strong assumptions that are present in basically most of these systems, and these are reliable communication, point-to-point interconnections, and authenticated messages. So on paper, this is great, right? So this makes the life of the protocol designer easier, but in practice, these are often implemented by the typical network stack, right? And these do not necessarily behave in the manner that the original designer envisioned, like with 0 latency. So of course there's some twerks to that. So our goal is basically to check out how we can optimize these. So we can see that reliable communication point-to-point interconnections are usually implemented by TCP/IP, and the assumption of authenticated messages is usually modeled by using signatures, message authentication codes, or even employing complete secure channel implementations such as TLS. In the talk here, we will mostly focus on the top half, so discuss the networking layer. So as I said, basically since 40 years or more, there's research going on how consensus and state machine replication protocols can be made more performant. So of course, we will have to choose some related work to compare to, so we will focus only on the related work which actually did study commodity network transport. So we have a couple of examples. So the studies were mostly regarding the comparison of well, TCP and UDP, how the different consensus protocols behave if they're flooded with different traffic. So in this case, the impact was mostly attributed to the implementation, not actually to the protocol. There was multiple discussions and models of the impact of UDP on PBFT, because PBFT was originally modeled using the UDP protocol. But of course, if you use UDP and you have unreliable communication, and this limits the performance and the robustness, because if a message gets lost, this is basically interpreted as a faulty replica, right? There have been probabilistic studies of the impact of TCP and UDP, studying or theoretically modeling and simulating the performance impact of using these protocols for even high loss values up to 30%. And of course, there was a significant performance impact. But all of these related work didn't really go into more details what can be done on the network layer to optimize, for example, in terms of configuration and other transport protocols. So that's what we are aiming to do. Also, another mention is basically that since there has been, I would say when I started my research, there was a lot of modeling and a lot of theoretical work, and some protocols actually published real-world systems and did measurements. And now there seems to be a lot more interest in actually focusing on the limits and effects of practical implementations. So also for longest chains, like proof of stake consensus, Joachim Neu and his colleagues published a paper that tried to address basically the gap between these harsh requirements and real-world implementations for robustness. What about the general bottlenecks regarding the performance? So the general consensus in literature is that in leader-based system, the leader is the system bottleneck node, but on other sides, basically the statements really diverge. So it really depends on the actual system, it depends on the environment. So some papers identify network communication to be the bottleneck, other papers identify the OS stack, the networking stack, as to be the bottleneck. Other papers identify crypto to be the bottleneck, again, depending on the environment and the actual protocol. So since this is so diverse, to make basically a study, we have to narrow our focus and choose one example, and this is what we're going to do. So for this presentation, we'll take a look at hot stuff, which is a leader-based BFT-SMR protocol designed for partial synchrony. So why did we choose hot stuff? Because it's used in a lot of ongoing studies, and it's base for practical systems such as Cypherium or Deem, which was for a Libra or Libra coin. And such as the other protocols that are basically listed before, it also assumes authenticated, reliable, and point-to-point connections. It does the implementation through typical TLS, TCP, IP channels, using elliptic curves to sign votes and proposals. So we can see it looks a little bit different than the PBFT approach. It's a leader-based protocol, so roughly, let's go over it. We have a client that requests something from the replicas, and in the end, the replicas will answer the client. If it gets enough answers, then it accepts the thing that it wanted to replicate as successful. And then we have the actual consensus algorithm conducted in 3 phases or views in the middle. We can see the structure is always the same. We have the leader sending some proposal and the replicas voting on it. And then in the end, if the leader gets enough votes, he can continue to the next phase, basically. So let's check if we can reproduce the claims that we have found in literature. Well, if we split up these communication patterns into flows, so basically we have the client communication, 2 replicas and back in flow 1 and 4, and the consensus communication in flows 2 and 3, so the votes to the leader and the proposal of the leader, then the question is, well, what is the performance properties? What can we see? Well, the first thing, of course, that we see is that, of course, the client and the leader are bottleneck nodes, right? So these are nodes where a lot of stuff happens. There's high transmission and processing volumes, so the leader has to process a lot of votes in the cryptography, aggregate the signatures, for example, and the client has to handle all the payloads. So a small note here, in a lot of modern protocols, usually the actual operation payloads that are requested by the client are usually only sent between the client and the replicas, and the actual agreement on the things, on the commands, is done only over hashes. So also in newer papers, there's generally this division between that the systems try to decouple basically this transaction distribution and actual consensus. So what can we see? Well, considering this information, we see that the payload strain is typically bigger for the client. We have some traffic spikes depending on the round. So if the leader gets a lot of votes, there's a spike. If the client gets a lot of answers at the same time, there's a spike. And the crypto strain is usually bigger for the leader, right? He has to verify the votes, the signatures of the votes, and he has to aggregate the signatures for the next proposal. What we were also talking about was transport channels, right? So what happens, for example, if we use UDP? Well, if we use UDP, then we don't have reliable communication anymore, and this is one of the base assumptions of the protocol. So is there actually an effect if we have lost messages? So if we consider all of the flows again, then what we see is basically that hot stuff in itself does not provide a way how the client can, or the replicas can recover if the messages get lost on client replica communication. So if a message gets lost in flow 1 or flow 4, then client or replicas might actually desync and they might not recover. So this is of course a big problem because it would be a safety violation. So we can directly see just using UDP wouldn't work. For the general voting process, if a vote is lost or a proposal is lost, well, then it affects exactly this round in case of a vote, or it affects exactly the replica for which the proposal is lost until it catches up. So in this case, the protocol actually implements something which allows the replica to request missing information from other replicas. So in short, what we can say is that in general, if we just were to violate, of course, the assumptions that we need a reliable channel, then we potentially, of course, compromise safety, but we definitely reduce performance. So what can we do? We can choose different transports to connect the different replicas in the protocol. So for example, in our paper, we used, this is a subset of the protocols that we used, for example, UDP, TCP, and SCTP. If we compare them on paper for the general characteristics, we end up with something like this. So generally we see, well, TCP and SCTP have a handshake, UDP does not, so the initial latency is pretty small, but again, if the system is running for a long time, this doesn't matter too much. We have considerable or bigger payload overhead for TCP and SCTP, least overhead for UDP. Again, if you have a very high throughput, then this packet overhead might actually matter. For sparse writes, it might not matter too much. Regarding the processing overhead, it is actually nice that you have protocols such as SCTP or other configurable protocols where you can selectively disable some features, such as ordering. So this is not possible with TCP. And then, of course, if you're using UDP, you might exceed the MTU of the link, causing IP fragmentation, further security and performance issues, and generally you would end up with safety loss. So considering that, of course, just using UDP is not a nice answer to our problem, how to improve the network layer, what can we do? Well, we can try to optimize how the more elaborate or the more reliable protocols such as TCP or SCTP are working. So there's different dimensions how we can configure this. One of the first dimension is in terms of delay and coalescence behavior, right? So consider the following example. We have a sender and a receiver, and the sender has some writes, for example, system calls that he issued. And then the operating system might merge them, and then the receiver at some point will acknowledge. So the optimization dimensions that we have in this case are first, of course, the sender might merge multiple writes or delay them until he can merge it to prevent more protocol overhead. And the receiver can actually introduce more response delay to, again, reduce protocol overhead. So what does it help us? Well, option 1 reduces the protocol overhead mostly for small writes, right? So this means that because only small writes can actually be merged together, if basically the packet is already full from the whole payload, there's no need to merge. So if we do merge small writes, then we have increased latency for some small single writes. If we use the optimization mode 2 and we reduce the protocol message overhead for long receiving streams, well, then this might mean that there's increased responder latency for sparse incoming writes or if we're at the end of the data stream. Of course, as I already said, these options are only available if you're actually using a protocol that has this kind of options. In this case, also SCTP provides more flexible configuration in user space. So on paper, okay, but what does it mean for BFT-SMR protocols? So let's basically apply these theoretical optimization modes to the hot stuff scenario. So here in figure 7, we can basically see one of the typical flows. So the situation from flow 1 and flow 4, we have a client and replica communication. The client is sending some comment requests to the replica, and at some point he gets an answer. So what happens if we actually apply these optimization modes? Well, if we are coalescing different writes, for example, using autocorking or Nagel's algorithm, well, then this is only triggered if these comment requests are very small, right? So, and if it's triggered, then the latency for these comment requests might be increased. So if this replica is batching the requests, which is done in a lot of protocols nowadays as an optimization measure, then this might delay the batching process. If the comment request is bigger than the segment size, well, then we don't care because the coalescing is not happening. What about the receiving delay? Well, one possibility that you can use, or one technique, is the delayed acknowledgements, which basically only sends explicit acknowledgements for every second received segment to reduce protocol overhead. But it interacts very badly with Nagel's algorithm because both sides are essentially waiting on the other side to send anything, right? So it introduces more latency. What about the other flows in hot stuff? Let's consider, for example, replica-to-replica communication here in figure 8. We have a leader on the left side and a replica on the right side. The leader sends some proposal, the replica votes. If the leader got enough votes, he can send the next proposal, and so forth. So for this communication, what happens if we apply this optimization modes? Well, for sending coalescence, again, typically the size of the proposal and vote messages are bigger than the segment size because of the signatures, right? So at least hot stuff and most protocols are using some form of asymmetric cryptography. So if you're using some MAC that is very small, that might work. But in most cases, actually, the messages will be bigger than segment size and the coalescence will not help. Also, usually consensus protocols are operating in terms of a lockstep fashion, right? So the leader is sending something, the replica is sending something, though the communication is alternating, usually, most of the time. What about the receiving delay? Well, since we're operating in this lockstep mode, the acknowledgements can actually be piggybacked to the messages that are there. So this situation that we have a basically a simplex stream for a long time in one direction doesn't really occur. So long story short, what can we say? Well, this dimension of optimization only makes sense if we have small payloads, right? If we have small payloads, either for the requests or the votes or the proposals, then we should disable this coalescence to improve latency, and of course configure the delayed acknowledgement bounds for the network environment that we're in. Another component of optimization for reliable protocols is, of course, retransmission, right? Because if a message gets lost, then we need to retransmit it somehow. This is also something that we can configure through the retransmission behavior. So consider, again, an example from hot stuff in this case. So we have a client that sends some comment request to a replica, and then the comment request 2 gets lost, right? And in this case, the replica tries to tell the client, well, I didn't receive it, I'm only acknowledging 1, but also these acknowledgements are lost. So now, after some time, the client actually retransmits the first comment request because the retransmission timeout occurred. So why is this relevant? Well, because we can configure it. So the configuration of the retransmission timeout basically trades response latency against early timeout. But typically, the consensus decision latency is way, way, way smaller than the RTO. So if we have like TPS in a permission blockchain of multiple thousand decisions per second, then of course a retransmission timeout of maybe 200 milliseconds introduces a very big latency, right? So what we want to do is we want to configure this accordingly. Another thing is forward RTO recovery, which basically just tries to detect spurious retransmission timeouts and configure congestion control such that the throughput of the channel is not reduced. Okay, so summing up, what we can do in this dimension is we can optimize the RTO bounds for the target network because it may yield reduced latency and also better throughput if the network in which we're operating is actually, well, if there's loss, right? And the actual values, of course, depend on the round trip time of the network, the loss rates, the congestion possibility, and so forth. So the more you know about your private network, the better you can optimize, essentially. Okay, so to sum it up, the key points. So we try to outline the feasibility and impact of building block optimization for BFT-SMR systems. We showed systemization of practical BFT-SMR systems in terms of their networking architecture and general assumptions. And we did a small optimization analysis of the network transport building block, including a hot stuff case study. For this, we found that transport protocol type can have a significant influence on the operation, and that the configuration is important, especially if you're operating in edge cases, so if you have small payloads or operating in lossy networks. And then it definitely makes sense to take a look at this layer. And the influence is most prominent, of course, on bottleneck nodes, if there are any. Future and ongoing work, we're currently in the process of quantifying or submitting a quantification, publishing the quantification of the presented impacts through reproducible measurements at our chair. And we're also investigating other networking layer related behavior regarding secure channel implementations, and of course also other general BFT-SMR building blocks, such as different cryptographic algorithms. 20 minutes, that's it. Thank you very much. Questions?
Yes. Any questions from the audience? Yes. One question.